looked at mostly, just so you're aware, and I plan to probably review the same ones with you guys, was number, nope, not from that one. It was the last two. So it was number 35, which was show that the ratio of the kinetic energies before and after the collision are particular expression. I thought it was useful to I spent probably a good 20, 25 minutes describing that and going through it. I think there's actually a fair amount to learn from that. That was important. And then 40 was the one, the last one with the table and the block and the bullet, this one here. So I intend to go over those two.
I had trouble with 35 because, like, I didn't think we could use the kinetic energy equation since it was inelastic.
Right. Yep. So I'm going to go over that one. That was the first one I said that I'll be reviewing.
Okay.
Yep. 35 and 40 for sure. I will spend time going over, and then you can let me know if there's others that you guys wanted. All right. So I'll give you some time. Touch back in about 15 minutes, give or take. All right, guys. I think it's a good time to get started. You can hear me, I think. Yeah. Okay. So let's. I'm going to start the round a little bit. So I'm actually in Mr. Marzak's room, so I have a smart board that's working. I'm going to use it.
Is that why your background looked different the other day?
I don't even remember. Yeah, the last few days I've not been in this class at all. They're doing work in my room. I don't even remember where. I've been in all sorts of different. I'm moving around class to class depending on which rooms have been available. Yeah, that's 100% correct what you just said. All right. All right. Actually, I'm going to just go over. Well, no, I'll ask. So, which problems would you have liked to review other than, again, I'm going to go over 35 and 40. Yep, I'm definitely going to go over 35 and 40. Are there any others? Even if there are, I may or may not be able to get to it, but I could always, record myself at some point reviewing it. Yeah. 25A. So let me take a quick look at it. Yeah, books are, like I've said, they can be a little wonky how they go about solving stuff. Not that it's wrong. It's just a second. Would you just say 25?
Yeah, 25.
Okay. I could probably do that one relatively quickly. Probably. Yeah. I mean, I don't know that I'll do the whole thing because I definitely want to get through 35 and 40, but I can certainly at least show you how to set it up and what the main steps would be. Okay, so let's try that. So for that particular problem, you have some person that's throwing something that originally they have initially no speed. So they're just floating in space. They have no speed. They take a tool or a tank or whatever it is and they throw it. Did they give you the speed that they throw it at? I think they did, right? They throw a tank. How fast did they throw it? Was it 8 or 12 meters per second or 8 meters per second? And then we would have to know, what is the mass of this tank? 12 kilograms. Okay. So the idea is that if this is the spaceship all the way over here, I mean, no square spaceships are out there, but let's just imagine there are. If this is the spaceship, then when she or he, whatever it is, throws the tank to the left, she's placing a force on the tank. The tank's feeling a leftward force, but Newton's third law says she should feel a rightward force, right? Simultaneously. And that force that she feels depends on how fast she can throw it. If she can throw it really, really fast, well, throwing something really, really fast takes lots and lots of force, which means that lots and lots of force will be returned back onto your body, and that would kick you towards the spaceship with more speed. On the other hand, if if it was my son who 5-year-old kid can't throw that fast, he won't be able to generate so much force between his hand and the tank because he's weak. And so he would still be kicked to the right, but with less speed, although he's lighter. So that would be a whole nother layer to this. But that's the general idea. This is a momentum problem. And so you would say that the momentum, the momentum initially has to be, this is really a sum, equal to the sum of the momentum after. But they're not moving. So if they're not moving, this is really like the explosion problem, where you're looking at something that's not moving or a system that's not moving, and then all of a sudden one part's moving to the right and one part's moving to the left. So this is similar to the skateboard problem where they had the kids sitting on the skateboards or whatever it was for the Pivot Interactive Lab, and they pushed off of each other and they go flying to the left. Same exact approach. So we know that after they are thrown, we have tank going to the left, and then we have the tank. We have the person going to the right, and we know those have to add up to 0. It just simply means that if the tank's momentum happened to come out as negative 100 units, that the person's momentum would have to come out as plus 100 units. plus and minus just based on their direction. Person's going to go to the right, tank will go to the left. The magnitudes should be the same. They have to have equal magnitudes, not equal speeds because they'll have different masses, but the magnitudes of the momentum should be the same. So with that in mind, you can really, not great. With that in mind, you can just set the magnitudes, if you wanted to, of the momentum of the tank should be equal to the momentum of the person. So you'd say mass of the, oh, come on. So we would say mass of the tank times the, I'm just going to say speed of the tank has to be equal to the mass of the person times the speed of the person. I'm just using absolute values there to indicate, magnitude of velocity to speed. In magnitude, their overall momentums have to be the same for the tank and the person. So if you were given the mass of the tank and you were given the velocity she threw the tank at, and you know the mass of the person, you can determine what the speed of the person is as they coast all the way back to the ship. Did they give you the distance to the ship? They would have to. Okay, gotcha. So what you would have to do is plug all these numbers in for mass of the tank, speed of the tank, mass of the person, all numbers, and you'd solve for the velocity of the person. I have no idea what that comes out as. What's the mass of the person? 80 what? 87. So we'd end up dividing both sides by the mass of the person. And so we'd have to work out what the ratio of 12 mass of the tank divided by the mass of the person, I don't know what 12 over 87 is. And then we'd have to, that's what these two pieces are right here. And then I'd have to multiply it by how fast the tank was thrown, I guess, which was what, 8? So it looks like 96 over 87, so a little over 1. I don't have, let's see, what is it? 1.1? Okay, so that tells us that the person will have a speed to the right. She's going to be now drifting at a constant speed because she's in outer space. After her, the tank leaves her hand, she'll move, absent of any forces, which in outer space there are none. She's just going to, an object in motion will continue moving in a straight line at constant speed. That's Newton's first law. So she'll move at a constant speed of 1.1 meter per second. Since we're referencing constant speed and we have, again, a speed, her speed, we need a time of 2 minutes that she needs to return. Presumably she's going to run out of oxygen. I'm assuming that's how they worded it, within 2 minutes. Then we have to have a formula that ties together distance, speed, and time for constant speed motion. That's just x equals v times t. So now we would solve for x. X would represent the distance between her and the spaceship. We would just plug in the v of 1.1 meters per second. And now we'd have to multiply by however many seconds. If it was 2 minutes, I suppose we'd have to plug in 120 seconds. The seconds and seconds would cancel, and we'd end up with a unit of meters, and the answer would be 1.1 times 120, which I guess would be 12 plus 120, so 132, which is pretty far. I mean, that's 1 1/3 football fields. Okay, all right. So I'm going to go to anybody else at home. Any other questions on how to do that? In fact, I'm not trying to overlook that. I'm just rushing a little bit just because I know the other ones, they take actually a long time to go through. So I'm not rushing because I'm overlooking it. I'm actually going to point out you guys need to know how to do that because that's a very common question. And it turns up, again, whether it's an astronaut like this throwing something to the left, or it's a person on a skateboard standing next to another person on the skateboard and they push off of each other. Or another variation I've seen is one of the little carts, like the ones I have in my room, is sitting on a track right next to another cart sitting on the track. And there's a little, spring that's in between the two cars and it's been compressed. And then someone lets go of it and they push off of each other and go flying off in different directions. You need to recognize that those are all the same problem. Those are exactly, they're, presented in different ways, but the process and what I just did is the exact same in all of them. They're all exactly the same. Also pointing out, right, the concepts of this problem, which are, if she is able to, well, actually, I already reviewed those. I think the main idea, other than the idea that if she's heavier, if it was a person that was much, much heavier, who also throws this bottle or whatever tank at 8 meters per second, then they're not going to be coasting to the right with a speed of 1.1 meters per second. They're heavier, right? So during the throw, the force that's generated between their hand and the container, which is the same as the container back on them, that will cause less acceleration on their body because they're heavier. And that acceleration, again, would only last for a few fractions of a second during the throw. But they would definitely, the heavier person would come out of this with less than 1.1 meter per second of speed, right? And they would coast at a slower speed towards the spaceship. Or again, if they throw it faster, then it will create, generate more force in between them, and the person would coast to the right with more speed than 1.1 meter per second, right? Or if I guess it could even say, what if the bottle was lighter? The container is lighter this time. She still throws it at 8 meters per second, but it's not a 12 kilogram bottle, it's a 5 kilogram bottle. Well, if it's going the same speed, but it's a lighter bottle, then that bottle now has less momentum going to the left than the current one. And that means the person will also generate less momentum for themselves going to the right. And if all else, other things are equal, then they would have less speed as a result. Assuming, again, that the lighter one is thrown at 8 meters per second. Practically speaking, if I throw a heavy container at 8 meters per second and then you hand me a lighter one and say, throw it again as hard as you can, it ain't going to leave my hand at 8 meters per second. It's lighter, and I would presumably be able to throw it faster. Anyways, that's that. I'm going to now try to... sorry that I'm not... yeah. It's like I have multiple things going on. I have paint controls, and then the Epson has controls. I'd like to just close this. Can I just close it? Oh, come on. Unless there's I don't even know where shoot. Come on. All right. Should be just there you go. Where's the erase? Full erase? I don't even see. I'm just going to close it. Don't save. Oh, and now there's stuff all over my screen. Don't do that to me. All right. As long as it all works. Yep. It all works. So the next one is going to be 35. Number 35. Did you get out of the way for you? Yep, I can scoot in. So let's look at 35 is the next image, I believe. Yep, 35 right there. All right. It says, consider the ballistic pendulum. You guys are familiar with the ballistic pendulum now. And this question is, again, the ballistic pendulum is when a bullet is launched into a pendulum that usually has a piece of wood at the bottom, embeds itself in the wood, and starts to kind of swing on the upwards direction we did the lab, right? So you remember that. This is a specific question asking you to show what the ratio of kinetic energy is for the kinetic energy of the system before it collides with the block compared or divided by the kinetic energy of the bullet, in this case, coming in, divided by the kinetic energy of the bullet and the block after it's embedded, after they start to move to the right. So it's a ratio of initial kinetic energy before the collision divided by final kinetic energy, which is right after the collision. And they want us to prove that it's this ratio. So let's try that. All right. I wish I knew how to make that bigger. Although
there's a little dot in the corner. There's a little.
In fact, 1 second. I think there we go. Okay. Just going to use this one now. Okay. So let's sketch this up. So we have our pendulum, and we have a bullet, right? That's coming in. We know that the mass, I'm just going to call it mass of the bullet, I suppose. We don't know what its mass is. And it has some initial velocity. I'll write that as VI with a B, just to indicate it's the initial velocity of the bullet. Yeah, I guess I'll keep capital B for bullet. That's the initial scenario, right? The final scenario that we're referencing is just after the impact, that bullet is now embedded inside of this block of wood, and they're now starting to move to the right with what we call the final velocity. And it's for both of them, right? It's for the system. It's just, a couple frames after it's embedded. And they're asking us, again, for what is the ratio of the kinetic energy. So first, before we can do a ratios, we have to work out what are the kinetic energies themselves. So the kinetic energy of this bullet would be 1/2 times the mass of the bullet times the initial velocity of the bullet squared. When we try to create an expression for the kinetic energy in this situation just after it's been embedded, which I'm going to reference as Kf, because again, I and F represents just before and just after it's embedded. So Kf, for just after it being embedded, would be 1/2. Now, in this case, they're again stuck together as one object now. So the total mass is mass of the bullet plus the mass. I don't know, what should I call? They're both B's. Bullet, block, they both start with B. Yeah, let's do that. Good suggestion. I'll do a lowercase b for the block and capital B for the bullet. Probably should have been backwards, but whatever. So just know that the little okay, and then we have some speed. We don't know what that speed is squared, but that's referencing the speed that it generates just after it enters. Now, what does conservation of momentum do for us? Remember that conservation of momentum is a tool that allows us to reference just before and just after the collision, right? And usually in this type of collision, which is called an inelastic collision, usually the question is all about what is the speed, use the conservation of momentum for inelastic collisions to determine what the speed is of both of them after they stick together. That's usually what they ask. And in this case, that's actually what we're looking at, because this again represents the speed right here, just after they embed. And since we don't know what that is, we'd have to look to the conservation of momentum. So let's do that. So for momentum conservation, we would say the sum of the momentum before this collision should be equal to the sum of the momentum after the collision. In this case, we can't write 0 like we did in the last problem. This bullet's coming in with some particular momentum. So I'd write mass of bullet times the initial velocity of the bullet. I wouldn't bother writing the next term. What's that? Oh, I'll close them. Yep. I wouldn't bother writing the second term for the momentum of this pendulum before, because it's just hanging there. So that's why I've just not bothered writing it. The momentum afterwards, again, would have to be mass of the, added together with the bullet plus the mass of the block, whichever way it goes, I guess it doesn't matter, times whatever this final velocity is. I can call it speed. Everything's moving to the right. All motions are to the right, so I'm just going to call it speed. Direction doesn't really matter. Not in this problem, at least. So if I'm recognizing that this piece and this piece are the same. They represent the same. They represent the same thing. So that means I'm going to need to solve for V final in this bottom equation and plug it in on the top equation, that expression into the top equation. All right, So let's see if we can do that. When I use conservation of momentum, this is so, again, worth you knowing how to show it, the steps, and how to get it. Because again, it's very common that they ask something about this sort of situation. I'm just dividing on the bottom right. I'd have to divide both sides by the total mass. So it cancels out here. And of course, it would show up on the bottom. Right? So this is my expression for V final. And now, again, I have to go all the way to the top right of my whiteboard and plug it in for V final in the kinetic energy formula, the one that represents what kinetic energy they have collectively after they start to move together. Okay, so let's see how that goes. If there's any questions at any point, just yell it out. So I'm essentially just taking this whole thing, taking this whole thing and rewriting. Mass of the block plus the mass of the bullet. And now I'm stopping. And I now have to substitute in this expression for V final, not forgetting that I have to square it. What expression? This whole thing. This whole thing has to go in there now. This would be the mass of the bullet. Yeah, this could be. Yeah, did I start? Yeah, I knew that was going to get me in trouble. Sorry. So this should have been, I started changing lowercase b, capital B. Sorry, I don't want to try to confuse things. So this is really this right here in the numerator, this right here, this is representing the bullet. So capital B for bullet times V initial. I should be putting a capital B there, which I guess I did over here. All divided by this just total mass. So at least I've worked to figure out what an expression would be for the final kinetic energy, because I need that because they asked me to do a ratio. Before we do, we might as well just recognize that we're going to have to distribute our square. This is really raised to the 1. So that square would have to be multiplied by the 1 that's here. And our denominator is really an implied 1 there. We'd have to essentially raise the inner exponent to the outer exponent through multiplication. So I'd really have 1/2 mass of the, I'm just going to call it mass total, TOT for total mass. All right, so from that, it's just the total mass added together. It makes it simpler. The total mass multiplied by the mass of the bullet times the initial velocity of the bullet. That part, the numerator, has to get squared. Divided by, you want to think of it like this. Now the denominator would have to be squared too. I'm just going to call this denominator part, this part right here, just M total. It just makes more sense. Squared. Well, we might as well keep going. We have to simplify some things here. It looks like I have M total in 2 different spots. I have two factors on the bottom and then 1 factor on the top. So I can technically cancel out this one here with one of those. And that's pretty much it. That's all I see that I can simplify. So my final expression would be V. Sorry, I didn't mean to say B. My final expression would be mass of the bullet times the initial velocity of the bullet squared divided by 2, because my 1/2, I can just kind of tuck the 2 underneath, because it's multiplying by half is the same thing as dividing by 2. And then again, I have 1 factor of mass, the total mass here. So this is what I've worked so hard for, is an expression for the final kinetic energy of the block with the bullet in it. just after they collided. So let's keep going. Now I can finally do my ratio. At least I think I can. They said do the ratio of the final kinetic energy just after the collision and divide it by the initial kinetic energy of the bullet just before it collided. This is the ratio we were shooting for. Now let's just first think. If K final divided by K initial equals 1, what would that mean? If we work all this out and we get something in some stuff in the numerator, it's not going to be the number 1. It's just going to be a whole bunch of stuff in the numerator, and then you're like, oh, it's the same exact stuff in the denominator, so it's all equal to 1. If that were the case, what would our interpretation of that be? Yeah, you'd say that means they're both the same. That means the initial kinetic energy of the bullet is the same as the kinetic energy of the bullet in the block as they started moving away. You'd say, but that's not what we've been told. We've been told in inelastic collisions that there's always some loss, not of energy, energy is always conserved, that there's a loss of kinetic energy, that the kinetic energy physically decreases between the bullet and the block because some of it turns into vibration and sound and heat and whatever other stuff. So we know that our ratio can't come out as 1 because, again, we've been told there's been some loss of kinetic energy. What if our ratio comes out as greater than 1? How would we interpret that? What would our interpretation be? Yep, that means the numerator is bigger than the denominator. That indicates there's more kinetic energy in the block with the bullet in it than there was in the kinetic energy of the bullet itself. So how can that be? If the kinetic energy of the bullet is what's coming into this accident, how can it cause an accident with something and then have more kinetic energy after it runs into it? Like, that means we've just created kinetic energy out of nothingness. That's a violation of the conservation of energy, so that can't be. What about if it's less than 1? What would our interpretation there be? Keep going, Emma. Yep, that tells us this is a decimal, let's say, and a decimal indicates that the final kinetic energy in the numerator is smaller and the initial kinetic energy in the bottom is bigger, because a smaller number divided by a bigger number is a number less than 1. You say that makes sense because they've been telling us all along that the final kinetic energy is always a little less than the initial kinetic energy. So we're expecting to get a ratio that should indicate a ratio of less than 1. And to be honest, we'll see that the results aren't necessarily like a small effect. This is actually a really large effect. This isn't like, oh, it's like a little bit of friction, like most of the time we can ignore it. No, you're going to see it's a big result, and we'll see it in a minute. So let's finally do it. We have the final kinetic energy expression, I think, just sitting right here. Let's just write it in. MB times, this is again the bullet, times the velocity of the initial velocity of the bullet, squared, all divided by 2 times the total mass. And now I'm going to divide by the whole thing an expression for the kinetic energy of the bullet that was coming in. And we know that the initial kinetic energy of the bullet would have been 1/2. In fact, you can still think of this as 1/2 if you want up here. Those will eventually cancel. Times the mass of the bullet times the initial velocity of the bullet squared. And this again represents the bullet's kinetic energy. So what can we cancel out? The 1/2 divided by 1/2 goes away. And then we see, let me see if I can erase some more over here. The result of this ends up being something you're going to want to eventually write down after this, and just keep it in your notebook because it ends up being something you can use on a multiple choice question pretty easily. We still have to keep distributing. So there's a square here that needs to get pushed through both of these, right? So now I'd end up with mass of the bullet squared times the initial velocity of the bullet squared, just by doing that part, all divided by the total mass. And I might as well replace it with the way they have it. And now, again, the 1/2 canceled away. I end up dividing by something. But if I already have a ratio and I'm going to divide it by something, I might as well just multiply it by the reciprocal. And that's the last step here. Let's take what we have and just multiply it by the reciprocal. This is really over 1. So I can multiply by the reciprocal, which would be 1 over mass of the bullet times the initial velocity of the bullet squared. That's this piece here. All right, there's some more cancellations. There should be. I see that the initial velocity of the bullet, that's here. I'm sorry that I used 2 different subscripts for B. Oh, no, I didn't. I just did BI and then IB. But those both represent the initial speed of the bullet. Cancel, cancel. And I also see this is the mass of the bullet squared, and this is the mass of the bullet right here on the bottom, right here. So that means I can cancel that with the 2 on the MB squared on top. So what am I left with? I'm left with that. I'm left with the mass of the bullet, which was right here, after the square part got canceled with the other one that was in the bottom, divided by the total mass. Now, that's an awful lot of work, but the result is worth knowing because it will allow, they would never ask you to do that on the AP exam, never in a million years. I still think it's a good practice for people to see it, but the result is useful. First, let's check, is it a number less than 1? How would we actually use this? Will the ratio actually, for any collision that's like the one we've been told about, a bullet colliding with a block and embedding and then they move together, will this ratio of kinetic energies be less than 1? Which number will always be bigger, the numerator or the denominator? I didn't mean to do that, sorry. So we got mass of the bullet divided by the mass of the bullet plus the mass of the bullet. Which number will always be bigger regardless of what the masses are? I meant to say which side will be always bigger, the numerator or the denominator? Yeah, this will always be bigger. So it'll always be a smaller number divided by a bigger number, because these are the same, right? So it could be like 2 over 2 plus 5, and 2/7 is a number less than 1. It's a fraction, right? So that checks out. Now, let me point out one of the common questions that comes in on multiple choice, which I don't agree with them asking because it's assessing memory, pure memory alone. They'll give potentially a problem like this. They'll say a block is moving along. This guy is just stationary. And they'll give you the values. This guy has a mass of 1 kilogram, and this guy has a mass of 2 kilograms. And then when they hit, they're going to stick together side by side, and they're going to be moving this way together. They will probably give you a problem like that, and they're going to say, what is the ratio of the final kinetic energy of them together, moving together, divided by the initial kinetic energy of this guy? Well, let's just use it. The numerator, when I say MB, that's just the mass of the guy that's coming in. Use, in this case, 1 kilogram, divided by the sum of the masses, 1 plus 2, 1/3. So that tells us that the final kinetic energy is only 1/3 of the original kinetic energy. That's not minimal. If your final kinetic energy is only 1/3, how many thirds have been lost due to the collision? 2/3. Is that minimal? That's 66%, right? That's a huge difference. That's not, again, this isn't like a minor little thing. In that case, again, 66% of the kinetic energy of the incoming block is lost to friction and to heat and to sound and to vibration. It's like a huge amount. It's more than half. And then the remaining amount of kinetic energy actually maintains itself as translational kinetic energy as they move across the floor. So it's a huge effect. Let me lastly point out, what if it was applied to the bullet in the block? Let's try. Let's just for the heck of it, see what would the result be. Well, I think in a bullet problem, they said that the mass is 5 grams. 5 grams is only 0.005 kilograms. And if it embeds itself in, let's just say, a 1 kilogram block, what result would we get here? Again, so mass of the moving object, which is the mass of the bullet, which is 0.005, divided by the mass of the block plus the mass, it'll be like 1.005. That's going to come out as, I don't even know, it's probably like, actually I have it right here, calculator. 0.005 divided, 0.005 divided by 1.005. 0.00 times 100, I guess it's 0.4%. So that means how much kinetic energy does the block and the bullet have after it embeds? Only 0.4%, not even 1%. That means how much kinetic energy from the original bullet was lost? 99.6% of the kinetic energy of the original bullet is lost, and only 0.4% is maintained as the bullet and the block move to the right. It's a massive, massive effect. What's the only thing that I think you should write down and just try to memorize? And I don't like that. It's this right here. But the ratio of the kinetic energies, again, I know this is all a lot of messy stuff. You'll never be asked to do all of it. The ratio of the kinetic energy, K final divided by K initial, is the mass of, I don't know what to say, initial moving object. I mean, it's always the whatever's moving first into this inelastic collision, divided by the total mass. Just remember that the numerator is not the mass of the guy that's sitting there. It's always the mass of the thing that's moving into the collision. And that's super easy, because if they give you numbers like 1 and 3 or 2 and 4, which they will, you could technically solve that multiple choice question in like 10 seconds if you knew the formula. Super easy. All right. I'm going to try my best now. Any questions on that one? I'm going to try my best to do the next one. All right. There should be an all clear on this, right? Yeah, clear on this. Okay, so the next one is now a number 40, which is a block sitting on the edge of a table and a bullet flying along, and it's going to embed itself into the block, provide a force to the right on the block, causing the block to move to the right, fall off the edge of the table with the bullet embedded in it, and land here. They gave us some information. What was the original height? I know one was 1 and the other's 2. I don't remember which one was which. Height is 1. And the range, we call this the range, by the way. And this is a really good problem, because it's going to refresh us a little bit on some things we haven't talked about in a while. This involves trajectory, projectile motion and kinematics and stuff like that. So what we have to do, because they've asked us, the question is, what is the initial velocity of the bullet? If all that is known is the masses, and I would need those. What are the masses, Emma? Perfect. So they're saying essentially, with only this information, the masses of both, the height of the table, and the measurement on the range, based just on that information, what was the speed of the bullet? So what we're going to have to do is work backwards, right? They're giving us information all the way to the end, to here, which is the range. And we have to now work backwards through this problem. Following this, imagine the video going backwards, because the last thing we're interested in is over here in the beginning of the video. So we literally have to do math that starts in the end and reverse engineers back to the beginning. So we first start by saying, well, we know that, remember that the horizontal speed is constant. Once it goes airborne, these distances are equal per second, or per tenth of a second. For every equal amount of time after it goes off the edge, it will move sideways by an equal amount, because the horizontal speed is constant, because gravity is only a vertical force, and vertical forces don't affect horizontal speeds. Right? You guys remember that. So that means this is again, since this is constant speed, we can use the constant speed formula, which is just x equals vt, where x is really the range. X is just that in t seconds, t represents how many seconds it's in the air for. We'll tackle that afterwards. It should go a distance equal to whatever the horizontal constant speed is. We don't know it, but we can figure it out, times how many seconds it's in the air. And that total distance is usually called range. So I'm going to remove the x, which is more generic, and make it specific to this problem and call it range. Now we think, what about t? How would we have to figure out how long is it in the air for? Does the amount of time it's in the air depend on the mass of the block? Does the amount of time it's in the air depend on the mass of the bullet? Does the amount of time that's in the air depend on the initial speed of the bullet? I hope not, because then we're really screwed, because we would never be able to solve the problem because they didn't give us the initial speed of the bullet. Does the time that it's in the air depend on the height? Which one of those do you think it would depend on? Someone else, but thank you, Emma. Someone at home. Anybody at home? Say something so I know you're still there and you can still hear me. I hope. Hello? Hello?
Would it be the height?
Thank you. Good job. Is that Jaden?
Yes.
Yep, it's totally all dependent on height. Remember this important idea that when you drop a block or a rock or whatever from this corner, you just drop it, it's in the air for the same amount of seconds as the same rock being kicked sideways. They'll fall side by side. This one would be here, this one would be here. This one would be here, this one would be here. This one smashes here, this one smashes here at the same moment. They're in the air for the same amount of time. So when you're given this projectile, sideways projectile problem, which you will because it's one of the famous problems, you know that the time that it's in the air can be solved by just figuring out how long does it take to fall if it's dropped from rest. Well, that tells us we can just use distance equals 1/2 at squared, where d is the vertical distance, the height. So I guess I could just call it h, more specific to this problem. A would be g, because it's the acceleration due to gravity. And now I can solve for t. I'd have to multiply both sides by 2. Then I'd have to technically divide by g. And then the last thing to be done would be the deal with the square, and I'd have to square root it. So that tells us that there's an expression there for the time that it's in the air. Time in air depends only on h. I mean, it depends on g too, but you ain't going to change g unless you go to another planet. Just a side note, time is proportional to the square root of the height. So if it's dropped from 4 times as high, square root of 4, it's only in the air twice as long, not 4 times as long. If it's dropped from 9 times as high, square root of 9, it's only in the air 3 times as long, not 9 times as long. Just a side note. Now, can we technically plug this expression for time right here? Yeah, those two t's are the same. The range function that we have has t in it, and that represents the time that it's in the air. So let's plug it in. Oh, I shouldn't have erased that, but I guess I can write it down later. That means I'm now writing the range, eliminating t. I guess this in algebra is called the elimination method through substitution. I'm not interested in time. So I'm subbing in an expression for time from one into another equation in a system of equations, and I'm eliminating t. Let's see what we get. This piece represents time in the air. That's cool because that's a useful formula. If you want to jot it down, you can. Will you remember all of them? Of course not, but it might be someone's like, oh, I remember that, or you can derive it, but again, it takes time. So if you want to, that's the range formula for specifically for horizontal launch. Meaning when it comes off the edge of the table, which they like giving those ones, it's moving just horizontally. It would not be used for a true like football thrown in the air at an angle. This is not the right formula for that. This is specifically for horizontal launch. If they give you the height of the table, it always has a table in the AP problems. And they give you the sideways speed, Vx. Usually you have to solve for Vx because there's a block sitting on the edge of the table and another block comes in and smashes into it. You have to use the conservation of momentum to figure out how fast it moves off the edge of the table. And then once you have it, you plug it in right there for Vx and you plug in the height. Just pointing out that's useful. That tells us we can ultimately backtrack now. We're rewinding this video and pointing out we know the range. They gave it to us. They gave us the height. Boom. We know G. Boom. That means the only unknown is Vx. So let's solve for it. Looks like I would have to multiply by the reciprocal of square root of 2h over g because I'm trying to isolate Vx. So I would just multiply by the reciprocal of square root of now g over 2h. I just multiplying by that reciprocal. Is that worth memorizing? No, but the other one I probably would. I at least try. I mean, try your best. I mean, before you actually have the exam, I'm probably going to give you a page of all stuff that you'll be like, yeah, I remember seeing that, and then you just do your best. I'm not against doing memorization right before a test. I'm against teaching through memorization. That should never happen. You should never teach through memorization. You teach to understand, and then if there is a high stakes test, then you ask students, try to remember as much as you can, beforehand. So let's do it. The range was 2 meters. G is 9.8. The height was 1 meter. And that whole thing had to be square rooted. Does anybody have a calculator that could do that? 9.8 divided by 2. Where's my calculator? Can anybody tell me at home what that comes out as? 9.8 divided by 2, square root it, then multiply by 2. Anybody?
$4.43.
Thank you. Perfect. So 4.43, I'm just going to call it 4.4 meters per second. So that's the sideways speed that it has, the horizontal speed, which tells us that when it comes off the edge of the table, it has that speed. Right? So that is totally useful information. We now know, because this is so messy, I'm going to erase it, that it comes off of the edge of the table based on the impact with the bullet. It just leaves the edge of the table with a bullet inside of it, moving to the right with a speed of 4.4 meters per second. This is an inelastic collision, just like the one we did just a little bit ago. So let's use the formula for inelastic collisions. I'm not going to rederive it again, just because I don't think I have time to do that. But it's the same one we just looked at. The final velocity at this point, coming off the edge of the table, should be equal to the mass of the bullet times the initial velocity of the bullet divided by the total mass. We just did that. That means technically we have this. Check. I have the mass. Check. I have the mass. I have the mass. Check. The only unknown is the initial velocity of the bullet. Therefore, we should be able to solve for it and say we're done. All right, so let's give it a try. The initial velocity of the bullet should be equal to V final, which we now know is 4.4. That's sitting over here on the left. Multiplied by the reciprocal. So that would be M1 plus M2 divided by mass of the bullet. And all I did was take the stuff that I wanted to get rid of and just multiply by that reciprocal. All right, let's finally try to finish. Final velocity coming off the edge of the table was 4.4. The total mass would have been, I erased it. What was the masses again? So 258 grams. That 250 and 8. Yep. So 258 grams. I'll write that as 0.258 for kg, kilograms, divided by 0.008, because 8 grams for the mass of the bullet is 0.008. So that's our final calculation. 0.258. 0.25, clear. 0.258 divided by 0.008 times 4.4. I get 141.9. Is it a reasonable answer? Yeah, it's a bullet. I mean, it's a bullet. That's certainly, when you multiply meters per second by 2, give or take, I think it's 2.21. But roughly speaking, a meter per second speed times 2 gives you a rough estimate on that speed in miles per hour. So that's, upward to 300 miles per hour. It sounds right. It's the speed of a bullet. Could be certainly a lot faster than that. It's rifle or sniper rifle. But. All right, to be honest, I actually didn't think I was going to get through it, but I did. In fact, with even 8 minutes to spare. Surprised. I was hauling. Hopefully not too fast, though. Hopefully not too fast. All right, let me see. Try to find where you are. There you are. All right, do you guys have any questions on... do you have any questions on any of it? Just trying to see, is there another camera? I guess I don't even know how this all works in this room. Where's the camera? Oh, were you guys seeing me stand the whole time? Is that what was happening? Oh, I didn't realize that. That's the camera over there. Huh. Okay. All right. Hopefully that was helpful. If you have other questions, you certainly can, let me know. I can do my best to answer. Generally speaking, quizzes are really high. I'm hopeful that that's representative of true understanding. Probably is for the most of you. I mean, that said, I know that you're taking these things at home and there's always that possibility, but the last few quizzes, most people are getting 95s and 100s. So that's good. It's very good. I feel good about that. I will say also that I recently marked them as complete. So I'm pretty sure for quizzes, like at least the ones that I've given you that are considered progress checks. For progress checks, it at least shows you all the answers and all of the steps only after the teacher has marked it complete. I did do that the other day and marked all of them complete. So you should be able to log in if you wanted to see one particular problem, and it should not just show you the answer for all of them, but a full-on description of step-by-step on every single one. So just be aware of that. Saturday morning, 8 a.m. I won't see you guys tomorrow, but 8 a.m. hopefully you guys are all ready to go. Know that it's not high pressure, right? This is not high pressure. Totally not. Just do the best you can. I mean, do you really need to sit and study for it? If you want to, you can. But I'd say, to be honest, if I was taking it, I'd be like, I actually don't think I'm going to study at all. I just want to see, like, how much do I know? How much do I actually know without, like, staring at a book, right? Because that gives you a good baseline for what you know. Like, you won't know until the report comes back, but you're like, I guess I know that. Because that's a better way of determining what you need to then stare at for a little while before the real test. So that's my recommendation to you. And then, like I said, just more than likely, there's a couple two-dimensional problems about momentum. I'm going to record probably tomorrow during your test. I'll post those as homework. I guess a couple other things. Check your email. I sent you the codes, the join codes already. That is a unique code specific to you. Quite literally, they sent me an email with your name on it, with your code. Not meant for it to be mixed at all, so hold on to it. That's your code, again, to log into Engage to submit your answers. I'll obviously be with you the whole time, so it's not like you have to memorize any of that stuff, but I did want you to be familiar with it. The links won't be sent out until we all get together at 8 a.m. Right when we're ready to start. I'll then send the links out. Again, just click on Google Meet, because I realized I can run 2 Google Meets at the same time. So just log into Google Meet the way you always do. What else is there to say? I guess there's nothing else to say other than next week we'll be starting rotation. We'll be moving on. It's the last unit. I guess I'll say, someone asked me how much time would you like for rotation? I like 6 weeks. Typically, I like 6 weeks. It's a big unit, to be honest. Joey's shaking his head. Yeah, 6 weeks. Turns out that I think the exam is like either 6 or 7 weeks from now. So at least I know it's there. The time is there. We'll have it. We'll get through it. But that said, I don't know, is there going to be a week or 2 weeks to just be like, all right, we're done. Now we're going to practice for 2 weeks? Probably not. But that said, I will be giving you guys practice stuff probably relatively soon, so that weekend homework won't be rotation stuff. Weekend homework is actually going to be review homework. It's going to be assignment, problems from all over the place. And so you should get 4 or 5 weekends in a row where the assignment is a mixture of everything, so that by the time that time rolls around, you've had, been forced to do some weekend homework that helps you review. Lastly, if you haven't, still a good book, I think. The AP Princeton Review for all of your classes is pretty good. I like it for physics. A fair amount of the review stuff I do give you on the weekends will probably come from those Princeton reviews. I have them, although I haven't bought it for a while. So I think they update it with different problems each year. I think mine's like 4 years old or 3 years old. But just pointing out, that's stuff you can buy from Barnes and Nobles for $20. Or my recommendation is if you buy stuff on Amazon, buy it used, and you can get it for like $4. But somebody who opens it up and says, "I don't want this," and they send it back, and then all of a sudden it's posted for used for a third of the price. That's my recommendation. Anything else from you guys? All right, I'll see you guys bright and early Saturday morning. Bye-bye. See you later. Bye-bye. Oh, I can't wave to you because you can't see me. Now you can see me. Bye, everybody. Bye-bye. All right, bye-bye.
Bye bye.